Before we try our algorithm on several other subtraction problems, I want to define certain things. In every case, in every problem that we're going to do, the subtrahend number is greater than the corresponding minuend number. When that happens, in subtraction by subtraction, borrowing and carries are required. In our algorithm, we're going to do subtraction by addition, and there will be none of that. 3 is greater than 0, 9 is greater than 7, 4 is greater than 1, 8 is greater than 6, and so on all the way down. The other thing is that our algorithm, we're not concerned at all with the minuend. All we're going to do is add that 1 to that 8, and that is the simplest addition there is. If you add 1 to a number, you just get the next highest number. So it hardly qualifies as an operation. We're going to add 1 and 8, and we get a 9. We are very concerned with the subtrahend. We have to convert it to its 9's complement. We can do that mentally. We can ask the question, what number added to 9 equals 9? The answer is 0. Sometimes you can figure it out mentally. Other times you would go up here to the 9's complement table and look it up. 18 minus 9. 1 and 8 is 9. 9's complement of 9 is 0. 9 and 0 equals 9. 18 minus 9 equals 9. That is the correct difference. 10 minus 3. 1 and 0 is 1. 9's complement of 3 is 6. 1 and 6 is 7. 10 minus 3 equals 7. That is correct. 17 minus 9. 1 and 7 is 8. 9's complement of 9 is 0. 8 plus 0 is 8. 17 minus 9 equals 8. That is correct. 11 minus 4. 1 and 1 is 2. 9's complement of 4 is 5. 2 and 5 is 7. 11 minus 4 equals 7. That is the correct difference. 16 minus 8. 1 and 6 is 7. 9's complement of 8 is 1. 16 minus 8 equals 8. 7 and 1 is 8. 12 minus 6. 1 and 2 is 3. 9's complement of 6 is 3. 3 and 3 is 6. 12 minus 6 equals 6. That is correct. 15 minus 8. 1 and 5 is 6. 9's complement of 8 is 1. 6 plus 1 equals 7. 15 minus 8 equals 7. That is correct. 13 minus 5. 1 and 3 is 4. 9's complement of 5 is 4. 4 and 4 is 8. 13 minus 5 is 8. That's correct. 14 minus 7. 1 and 4 is 5. 9's complement of 7 is 2. 5 plus 2 equals 7. 14 minus 7 equals 7. That is the correct difference. So in every case, using our algorithm for subtraction by addition and the 9's complement procedure, we were able to find the correct difference. And we did it by addition. And we did only one operation. We found the 9's complement of the subtrahend. The minuend, all we do is add 1 to a number. Is this algorithm valid for all numbers? No. The subtrahend digit or number must be between 0 and 9, one of the basic numbers. The minuend number must be between 10 and 19. If either one is out of range, then the 9's complement procedure will fail. So this is a special case, valid for certain range of numbers. So what good is it if it's only valid for certain numbers. A student in the first grade who is learning addition for the first time, when they reach the level of skill when they can add two of the basic numbers that add up to 9, they can be taught to do subtraction by addition using this algorithm. They don't have to wait to the second grade or the third grade whenever subtraction is introduced. They can learn it almost simultaneously with learning of addition for the first time. Moreover, the algorithm will allow a student to verify the subtraction table. They don't have to memorize the facts in the subtraction table. They can do it by using this algorithm. They can verify the table, and they can also construct the table. In the next clip, we will construct a subtraction table, because the range of numbers that we're dealing with here, this algorithm, corresponds to the numbers in the subtraction table. The basic numbers, the largest number is 9. 9 and 9 is 18. So the largest number in the subtraction table is 18. Okay? Where did this algorithm come from? This handheld calculator, if I put in a number 15, there it is, shows up on the register as 15. But in an internal register, the number that's stored is in base 2 numeration. Base 2 numeration only has 2 basic numbers, 0 and 1. So 15 is stored in an internal register. The display shows 15 in base 10 numeration so that we can understand it. But that's not the way the computer is going to do it. When I hit the subtract function, this button here, this calculator knows that the next number I put in, it's to write the 2's complement of that number and store it in an internal register. So if I put in a 7, there it is. It doesn't write 7 in that internal register, it writes the 2's complement of 7. Then when I hit the equals button, right here, it will proceed to add the 2 internal registers, get the result, and then transform it into base 10 numeration, and it shows up on the display, 8. The computer did the subtraction correctly. So here's the point. When we do subtraction by addition, we are doing it the same way this calculator and every computer on the planet does it. It uses 2 complement arithmetic and computes the difference by addition. So where did this algorithm come from? It's a carbon copy of the way computers do subtraction. 2's complement arithmetic, we're using 9's complement arithmetic, but the procedure is exactly the same. Incidentally, in a later clip, we will modify our special case algorithm so that it's valid for all numbers. Everybody is aware that this calculator does subtraction for all numbers. There's no restriction. So we're going to do that too. Now in our next clip, we will construct a subtraction table to show that it really is quite easy to do using this algorithm.